Hello everyone. Welcome back to this lecture series on Design of RCC Structures. This is lecture number 13 in which we are going to study the design of two-way slab using limit state method. In the previous lecture, we discussed the design of one-way slabs using the limit state method. There we understood that one-way slab bent predominantly in one direction and transfer loads mainly along the shorter span. In today's lecture, we will study the design of two-way slabs using the limit state method as per IS 456, explained through a complete numerical example. In reinforced concrete structures, slabs supported on all four sides may bend either in one direction or in two directions, depending on the span proportions. When the ratio of longer span to the shorter span is less than 2, the slab bends in both the directions and is classified as two-way slab. In such slabs, the applied load is shared by supports in both directions and therefore reinforcement is provided along both spans. With this understanding, let us now consider a numerical example. We are required to design a simply supported two-way slab to cover a room with a internal dimensions 4 meter by 5 meter, supported on 230 mm thick brick walls all around. The live load is given as 5 kN per meter square with a floor finish of 1 kN per meter square. The grade of concrete is given as M20 and the grade of steel is Fe415. As well as the exposure condition is mentioned as mild. And the slab corners are free to lift. As in slab design, deflection control governs the depth. We begin by assuming a suitable span to depth ratio. Assuming span to depth ratio of 25, effective depth along the shorter span direction, that is dx, can be calculated by 4000, that is the span along the shorter span direction, divided by 25 will give the effective depth along the shorter span direction as 160 mm. That is 4000 divided by 25. With a clear cover of 20 mm and assuming the shorter span direction, the bar has 10 mm dia, overall depth of the slab D will be calculated as 160 plus clear cover of 20 plus half the diameter of the main reinforcement 5, which gives us 185 mm. Now the effective depth along the longer span direction will be dy, which will be computed as overall depth 185 minus clear cover of 20 minus 10 the bar diameter provided along the shorter span direction minus half the bar diameter provided along the longer span direction, which comes as 150 mm. In two-way slabs, effective depths along both directions are slightly different and must be considered separately. Now we determine the effective span in both the directions as per IS 456. Here along the shorter span direction, the clear span is 4 meter and the effective depth is 0.16, which gives 4.16 meter. As well as longer span LY, which is 5 meter clear span plus effective depth along the direction is 0.15, which gives the effective span along the Y direction as 5.15 meter. Remember, we are having the second condition also to check for the effective span, that is the center to center distance between the supports. Here the support width is given as 230 mm. If you are taking this case, you will be having 4 plus 0.23, which will be more than this value, and hence we are not considering that one. We are taking the minimum of those two directly. And these effective spans will be used in moment calculation as well as deflection checks. Now, why this slab is a two-way slab? First, we need to calculate the aspect ratio. That is, the longest span direction to the shortest span direction ratio, which comes around 1.25, which is less than 2. Hence, the slab bends in both the direction and therefore classified as two-way slab. Next, we calculate the loads acting on the slab. It all starts with the self weight of the slab. The overall depth of the slab is 185 mm, therefore 0.185 into unit weight of the concrete as 25 will get the self weight of the slab as 4.63 kilonewton per meter square. And the other loads are the live load acting on the slab, which is 5 kilonewton per meter square, and the finishing load of 1 kilonewton per meter square, which both been given in the problem. With all these values, we can calculate the total working load or the service load as 10.13 kilonewton per meter square. Using a load factor of 1.5, we can get the factored load of 15.20. And this is not 8.13. Sorry, this is 10.13. Now, don't forget, in slab design, all loads are considered per unit area, unlike the beams. And next, the bending moment and the shear force. In two-way slab design, bending moments are calculated in both directions, not like in a one-way slab where we'll be calculating along the shorter span direction alone. Here, the moment coefficients will be obtained from IS 456 tables. So, the maximum bending moment along the shorter span direction as well as the longer span direction will be calculated using the relation MUX will be equal to alpha x into WU into LX square, and MUY will be equal to alpha y into WU into LX square, in which the design coefficients, that is alpha x and alpha y, it purely depends on aspect ratio, the support condition as well as the corner restraint condition. Since the slab corners are free to lift, the coefficients will be taken from case 9, that is 4 edges discontinuous, wherein only the positive moment at the midspan will be considered. As the aspect ratio being calculated as 1.24, we need to get the value between 1.2 and 1.3, and then it has to be interpolated in order to get the value for alpha x, that is alpha x. So based on the interpolation, we got the alpha x as 0.075. Similarly, for alpha y, if whatever the aspect ratio, it remains constant as 0.056. So that has been taken into account. So calculating the value of moment along the x direction as well as the y direction of 19.72 kilonewton meter as well as 14.73 kilonewton meter respectively, we can check whether these moments are within the permissible limit or not. Now, the limiting bending moment will be calculated using the relation 0.138 FCK BD square. So, substituting the values with B is equal to 1 meter of 1000 mm, we get the limiting bending moment as 88.32 kilonewton meter. Now, the moment which has been calculated along both the directions are found to be less than the limiting bending moment of 88.32. Hence, the section will be considered as an under reinforced section. Now, the maximum shear force will be calculated along the shorter span direction, which is the maximum one, which will be WU into L by 2, that is LX. So, in that case, it is 15.2 into 4.16 divided by 2, which comes as 31.62 kilonewton. Next, moving on with the design of reinforcements. Since it is a two-way slab, we need to design the main reinforcements both the shorter span direction as well as longer span direction. Let us now design the reinforcements in the shorter span direction. In two-way slabs, reinforcements are provided in both directions, and however, the shorter span generally carries higher bending moment. Using the design bending moment, effective depth along the x direction as well as the material properties, the area of the steel can be calculated using the relation which is given in annexure G 1.1b of IS 456. So this is the relation in which mu will be taken as mux and d will be used as dx along the shorter span direction. And b, as we know, we are considering per meter length, it will be taken as 1000 mm. So substituting all the values, you will be getting a quadratic equation in terms of AST. So you will be calculating on solving that quadratic equation, we are getting the AST along the x direction as 358 mm square. Now this has to be checked for the minimum AST condition of 0.12% of the gross cross-sectional area. Here the gross cross-sectional area is 1 meter by overall depth of 185 mm, this D. We are getting that value as 222 mm square. And here the AST calculated is greater than the minimum AST condition. We can provide the reinforcement for the calculated AST itself. So assuming the suitable bar diameter, we can calculate the appropriate spacing for that bar. So using already we assumed the bar dia as 10 mm. The spacing of the bar will be calculated by using the relation area of one bar divided by area of the steel required into 1000. We'll get the spacing as 219 mm. Now providing 10 mm dia bars at 200 mm centers as main reinforcement, the AST provided will be 392 mm square. And this spacing should be satisfying the condition of 3 times the effective depth. Here 3 into 160 is the effective depth, which comes as 480 mm, and in no case that value should be exceeding 300 mm. So this spacing has been satisfying this condition. So hence it is safe under cracking condition also. Now we design the reinforcement in the longer span direction. So although the bending moment is smaller than that in the shorter span direction, so adequate steel must still be provided along the longer span direction to resist the bending and control cracking. So using the effective depth dy, the reinforcement required along the longer span direction can be computed. Again using the same relationship, exception is instead of mux we will be using muy and dx will be used replaced with dy. As always b will be 1000 mm square, sorry mm. So substituting the values, we will be getting the AST as 284, and again this is exceeding the minimum AST requirement of 222. Now already assumed the diameter of the bar that are going to be provided along the longer span direction as at 10 mm. The spacing can be calculated as 276 mm. So now we are providing 10 mm bars at 260 mm centers as the secondary reinforcement along the or main reinforcement along the longer span direction. Again the AST provided will be 302 mm square, and this has to be checked with the maximum spacing condition of 3D as well as 300 mm. So both it is satisfying. Hence we can provide the same reinforcement of 10 mm dia bars at 260 mm centers along the longer span direction. So after flexural design, the slab has to be checked for shear safety. As we know, the slabs rarely require shear reinforcement due to their larger width as well as the smaller depth, even though that check has to be done for all the cases. Now it will start with the nominal shear stress, which will be calculated using the relation VU by BD. Substituting the values, we'll get the nominal shear stress as 0.198 Newton per mm square. And the percentage of the tension reinforcement along the shorter span direction is computed as 0.25%. So from table 19 of IS 456-2000, with a percentage of reinforcement as a 0.25, and for M20 grade concrete, this tau C, the permissible shear stress, is being taken as 0.36 Newton per mm square. And that value is greater than this is greater than the tau V value. This is greater. This is greater. Hence, the shear reinforcements are not required. Next, the final thing is that we need to check the deflection control also. As it is a two-way slab, the deflection check has to be done in both the directions separately, and it has to be checked for the maximum span by depth ratio. So the maximum span by depth ratio relationship will be calculated with the value L by D basic multiply with the modification factors of tension reinforcement, compression reinforcement, as well as the flanged section. And again, as it is a slab and there is no compression reinforcement, we'll be taking Kc as 1, and there is no flanged section, Kf is also being taken as 1. So Kt alone to be calculated. For calculating the Kt, already the percentage of the tension reinforcement is known. So using the percentage of tension reinforcement, and Fs has to be calculated using this relation, we got that value as 220 megapascal. So with the value of the percentage of tension reinforcement and taken for the curve of 220 megapascal, the Kt value will be computed as 1.73 using the interpolation. Now substituting the value and L by D basic, since it is, we are considering it as a simply supported slab, this value will be taken as 20. So substituting these values, L by D maximum will be calculated as 34.6. And coming on to the shorter span direction, the effective span is 4.16 meter and the effective depth is 160 mm. So using this, we'll be getting the ratio as 26, which is less than the maximum span to depth ratio. Therefore, the deflection control is satisfactory along the shorter span direction. Similarly, the same thing should be calculated for the longer span direction. Again, using the same relationship, taking the difference of this AST and AST provided along the longer span direction, we are getting the Fs as 226. And again, going with the percentage of tension reinforcement along the longer span direction for two different curves of 190 as well as 240. And then after interpolating for 226 megapascal, the Kt value will be calculated as 1.78. And again, L by D basic remains same. It is 20. Substituting the values, L by D maximum will be calculated as 35.6. Now the actual L by D ratio along the longer span direction, which is having the span of 4160 divided by 150, which comes as 27.7, which is less than L by D maximum. And therefore, the deflection control is satisfactory. Now moving on with the reinforcement details. This includes the overall slab thickness, that is 185 mm. This shows the cross section and this is showing the plan. The bar diameter and the spacing along both the direction, that is the shorter span direction as well as the longer span direction, both in the plan as well as in the elevation, the section. The clear cover is also being shown right up. These details form the basis for structural drawings as well as for site execution. Now let us summarize today's lecture. Two-way slabs bend in both directions. Load distribution depends on aspect ratio as well as support conditions. The design steps includes defining the cross section, effective span calculation, load computation, moment calculations, flexural design in both directions, and shear and deflection checks. And proper detailing ensures safety and serviceability. In the next lecture, we will move on with the application of this slab in the form of staircase. Thank you.